Welcome back to Inorganic Chemistry. In this part of our Chapter 3 discussion of the reaction of coordination compounds, we'll look at square planar complexes. So far we've looked at the formation of complexes, we've looked at ligand substitution, we've looked at substitution for octahedral complexes and how the d electron configuration can contribute to the kinetics. We've also looked at the rate laws, the mechanisms, and the thermodynamics. In this section we'll look at square planar complexes. In our final lecture we'll look at electron transfer reaction mechanisms. So ligand substitution for square planar complexes, we have fewer spectator ligands. Here's our leaving group and here's our entering group. And the square planar complex we see has it's only 4 coordinate, and so the complex is open at the top and the bottom, and so an associative mechanism is going to be much more important for this type of ligand substitution reaction than we saw with the octahedral complex. Now there's still some complications of the reactions in that we could directly substitute the ligand with our entering ligand, but since we're in solution we could also substitute the solvent for the leaving group, and so that will contribute to the kinetics, the mechanism. And so the rate law here would be this first step, K1, and solvent, the concentration of solvent we don't consider because it's so large and basically constant, so that doesn't show up in our rate law. So it looks like we should have a second order reaction, but this simplifies to a pseudo first order rate law in most cases. So even though the associative mechanism is important because of the interference by a solvent, it looks like a first order reaction. Let's look stepwise what happens as we go through this associative mechanism. So let's say our entering group arrives from the top here. It will make a square pyramid intermediate or transition state. So this is the same transition state actually we saw before for the dissociative octahedral complex. It's also a 5 coordinate intermediate or transition state. And before we said, oh, the geometry doesn't change much, but in this case the geometry has to change to get the product, or else, well, I guess it doesn't have to change. We could lose the leaving group and get this seesaw geometry. But actually what has been observed is that the intermediate forms a square pyramid. So you can see that here, where our entering group starts to slide down, our leaving group starts to slide out of the square plane. Until we are left with a new square planar geometry, or square pyramid rather, where our leaving group is now in the axial position. where it will dissociate to form our new product. And as we went through this intermediate, the trigonal bipyramidal, transition state, we see that our ligands, our spectator ligands, have an important role. So here we have this spectator ligand is trans to our leaving group. These two spectator ligands are cis. So that C actually stands for cis, not for carbon. And this ligand is trans to the leaving group. After we go through this transformation, the trans ligand is still where it was, and the cis ligands are still where they were. So the geometry didn't change. However, that's not the only option. The transition from a square pyramid to a trigonal bipyramid actually does not cost much energy. And you can see that ligands that were in the square, in the axial position of the trigonal bipyramid can end up in, so I'm breaking bonds, but we're not actually breaking bonds going through here, we're just rotating bonds. So if I rotate the bonds correctly, I get one of the axial ligands remains axial, the other axial ligand came up into the plane of the square pyramid, which means that we could reverse the direction and have maybe this ligand begin to slide down into the axial position of the trigonal bipyramid. So by the time we're all done rotating bonds, we would end up with now what were axial ligands, now one is axial and one is planar in the trigonal bipyramidal complex. So this shifting of the ligand's positions, we're rotating the ligand's position, not breaking bonds, although I did that for the model, but in reality these bond angles can shift. And this happens at a rapid time scale at room temperature with many complexes, and this is called a fluxional. The geometry is fluxional, it's in flux. It's changing with time at room temperature. And this time scale is observable. If you cool down the complex, you can observe the two different geometries in, say, an NMR spectrometer. So all of that to say that in our previous lecture, we indicated that a dissociative mechanism for octahedral, making a 5-coordinate square pyramidal intermediate, retained the geometry. That's not necessarily true, because the square pyramid can go through a trigonal bipyramidal transition state and change the geometry. So another effect, though, of considering of the spectator ligands is to note again that some of those spectator ligands in the original complex were trans to the leaving group, and some of them were cis to the leaving group. And this is going to have an effect. The type of ligand that is here can affect what happens over here. This is called the trans effect. And there's actually two aspects to the trans effect. There's a kinetic aspect and a thermodynamic aspect. So in the kinetic aspect, we call it the trans-directing ability of a ligand. And what this is that these ligands are in order of transability, in order of how they can increase the rate of substitution of the leaving group. Okay? So this is an order of increasing rate of substitution for X if it's trans to the spectator ligand. So these are the spectator ligands, trans to X. Carbon monoxide, for example, will increase the rate of substitution of X compared to hydroxide. It would be much more slower kinetics to substitute a ligand trans to hydroxide. Another aspect of the trans effect is a thermodynamic ability, which is called the trans influence. And what this is, so as we see, the spectator ligands actually are involved in the reaction, and in particular that ligand trans to the leaving group can have an effect. So we call this the trans effect. And actually there's two aspects to the trans effect. One is a kinetic aspect, which is called transdirecting. And in this this series indicates that this ligand on the left of this series, which should look familiar, looks very similar to the spectrochemical series, ligands toward the left will increase the rate of substitution for the leaving group if it's trans to said ligand. So this is a kinetic effect, and therefore, for example, if carbon monoxide is in a square planar complex, it will cause the ligand trans to it to be quickly substituted, whereas opposed to hydroxide in a square planar complex, it will cause the ligand trans to it to slowly be replaced. A different side of the trans effect is a thermodynamic side, which is called the trans influence. And what this does is, if we look at the square planar complex, the metal center, our leaving group, and our trans ligand, they are in a linear relationship in the square planar geometry, such that the d orbital on the metal is going to be shared with both ligands. And if it's shared more with this ligand, the trans ligand, that will weaken this bond here, making it less stable and easier to break. So that's a thermodynamic effect when looking at bond energies. Okay, where does the trans effect, how can we use this? And I'll call this the trans effect and synthesis. So when we do a chemical reaction, we want to consider the kinetic and the thermodynamic aspects, and we want to get a product that will be stable and of the desired geometry. So we could use kinetic stability or thermodynamic stability to try to maximize our product. Let's consider an important inorganic molecule that's square planar, and that is the platinum complex, square planar complex of 2 ammonias and 2 chlorides. An overall complex is must be -2 charge. It's a platinum +2 complex, and this is called cisplatin. And this is a powerful anti-cancer drug, and so this would be a useful product to synthesize. On the other hand, we could make the trans complex where the amines are trans to each other, and then also the chlorides must be trans to each other. Again, this is going to be a -2 charge. So this would be transplatin, the trans isomer, and this does not have the desired anti-cancer properties, and so this geometry would not be the desired product. So we can use the trans effect to maximize the desired product. If we start with platinum tetramine and we add a chloride to this to substitute. Since all four ammonia ligands are the same, it doesn't matter, we'll just substitute one of them. For simplicity or consistency, I'm going to substitute this ligand here. So I'm going to put the chloride here, and then we still have an amine here, amine here, and an amine here. Okay. So we replace this ammonia with the chloride, and of course it's going to change the charges, but we also now look here, and our transdirecting ability of chloride is greater than that of ammonia, which means that this ligand trans to the chloride will substitute faster than this ligand, which is trans to ammonia, or this ligand, which is trans to ammonia, or this ligand, which is trans to ammonia. So this ligand here, trans to the chloride is more transdirecting, this will substitute faster. Faster than the other three ligands, and so when we add our second chloride, it will replace this ammonia and form the trans complex. So this synthetic scheme is not the way to go to get the desired cisplatin compound. Let's start then instead with the tetrachloroplatinate. And when we substitute one ammonia here, again, it doesn't matter, all four chlorides are equivalent. Just to be consistent with the picture up above, I'm going to substitute this lower right with the ammonia. Oh wait, these are all still chlorides. Oops. Okay. So this would be a 3- charge complex. This is a chloride here. And again, looking at for the next substitution, looking at our transdirecting ability, chloride is more transdirecting than ammonia, which means that this ligand is trans to a chloride, so it will react faster. This ligand is a chloride, it's trans to a chloride, so it will react faster. This chloride is trans to a chloride, so it will react faster. This ligand is trans to an ammonia, so it will react slower. So these three positions will react faster if we substitute an ammonia. So we're going to bring in another ammonia here. If we substitute another ammonia here, then the complex doesn't change. It would have one ammonia ligand. So that would be self-exchange, so nothing happens. But if we substitute here or here, we will make the cis complex. And so this would be the this synthetic scheme here would be the way to prepare cisplatin. And so we can use this kinetic effect to get the desired geometry. Okay, so that's an example of the trans effect from the kinetics, and looked at the mechanisms of square planar complexes. And that's as much as we're going to go today for square planar coordination compound chemistry. In our next lecture, we will look at electron transfer reactions of coordination compounds. Thank you.